So thank you very much for the introduction and for organizing the conference, actually. So I should start by saying that this is joint work with Ottmar Spinners. So let me summarize our result. I would like to present and sketch the proof a bit as follows. So let me just say we proved that the following is consistent. So do you hear me, or should I? Is it okay? Yeah. So let's summarize the result as the following. It's consistent that H is strictly less than the additivity of S0, the additivity of the Marchevsky ideal. So let me start by explaining these notions. So H actually was already introduced by Jörg Brendle in his talk. He mentioned definition by intersection of open dense sets. I would like to concentrate on the easily seen to be equivalent to say that H is the least number of maximal antichains in P omega mod finite, so of mad families actually, which cannot be intersected by a single real. So there is no single real for H many of the maximal antichains deciding which one is picked from each of these antichains. I will come back to this and draw a picture later on. So this is H, so the distributivity number of P omega mod finite actually. And what is additivity of the Marchevsky ideal? So let me first define the Marchevsky ideal. So S0, the Marchevsky ideal is defined as follows: a set X in, so for a set X subset of 2 to the omega, it is in this Marchevsky ideal S0 if and only if the following holds. Each perfect set can be shrunk to a perfect subset disjoint from it. Or using the language of forcing, perfect sets are branched through Sachs trees. So you could say if for each perfect tree, so condition in Sachs forcing, there exists a stronger tree such that the body, the set of branches through this stronger condition, is disjoint from the set X. Okay, this is the definition of the Marchevsky ideal. And additivity, you probably know from Chichon's diagram, for example. Additivity of ideal just means how many, so what is the least number of sets in the ideal such that its union is not in the ideal anymore, right? So this is the additivity. And so this says we proved that it's consistent that the distributivity number is strictly less than the additivity of this ideal. Okay, so what was the incentive of this actually? Because under some circumstances the additivity of other ideals connected to tree forcings like Laban-Miller is bounded above by H. It gives a consistency of separating additivities of different tree ideals, and this gives by a theorem of Ottmar Spinners and Cellach, I guess, right, that the converse relation for the cofinalities of the respective ideals is consistent. But maybe Ottmar will give more details about this in his talk. So let me just stick to this and state the theorem more precisely. So what we get, so in which model we get this actually. So the theorem is as follows. Let's start with a model of CH and let A be, let's call it increasing Sachs amoeba forcing. So I will give the definition in a minute or so. And let P omega 2 be the countable support iteration of such forcings A. So all the time in the respective model, what I will define the A to be. And then in the final model, so then in V P omega 2, this holds. So what holds? H equals Aleph 1, strictly less than additivity of Marchevsky ideal equals aleph 2 equals the continuum, and even more holds actually. So we know that the bounding number is large in the model as well. Bounding number equals aleph 2. The splitting number is large, but the covering of meager, so one of the things in Zichon's diagram, is small. So this stays small. So this is what we can say about, and maybe more, but I just want to talk about these things, and of course this is the most important for the result then. So let me now define what this increasing Sachs amoeba is. So A.
Give credit, it's not our fault.
Yeah, so it's so what was the paper where they Veličković, just by probably Veličković, where you Louveau, yeah. Okay, so the definition of the forcing is as follows. So A consists of conditions Pn, where P is a perfect tree, a condition in Sachs forcing, and n is a natural number, and with, in addition, increasing properties. So let me just draw a picture. So P could look like this. So it starts here as the first splitting, then there's the next splitting, and so on. And as it's already indicated by the picture, if we go through the splitting nodes in a canonical lexicographical way, so this is the 0th, this is the first, the second, the third, fourth, fifth, sixth, and so on, then the heights of these splitting nodes are strictly increasing. So this is what we demand. And the natural number n says, for example, let's look at P2, for example. If the natural number is 2, this would say we fix already this first splitting and this splitting and this splitting, so up to the, in this enumeration, second splitting node. So this finite part of the tree is fixed, and above we can still shrink. So it's like with Matthias forcing or Prickwick forcing, that these first finitely many splitting nodes are like the finite part of the condition, and then there's the rest, which gives promises how the finite tree goes on. Okay, so more formally, so this is the definition of what the set A is, what is the extension relation, as I already described. So if Pn is such a condition, then a stronger condition Qm is, so this is stronger if Q is a subtree, if the natural number m gets larger, so this, or equal. So this means you can fix more of the finitely many splitting nodes. Actually P and Q agree up to, in this enumeration, the nth condition, like in Matthias forcing, the nth splitting node. Okay, so you are not allowed to remove splittings down there, given by n, but then you can remove. So, and what is the generic object? You just put together all the finite parts for conditions which are in the filter. And what do you get? You get a generic Sachs tree, actually, which is also increasing, because all these finite parts were increasing. So what you get is a tree, which looks like this and has this property that the heights are strictly increasing. And there also, Ottmar in his talk will give more details. So as usual for this kind of amoeba forcings, they increase the additivity number. This is kind of just, if you look at the definition, to give a hint of the proof, is just because it's dense to shrink these upper parts, and so therefore it's dense to avoid Marchevsky null sets, and therefore you can avoid many of them, and this means the union of aleph 1, many of them will still be Machevsky null. So basically, but it's not quite the proof. So therefore, let's say we have gotten that this will be true in the final model. So what do I want to say next? Yeah, very important for the rest of the proof sketch I would like to present is the following, that we get this. Why is this? Because we add dominating wheels. So where can we read off a dominating wheel? It's just because, yeah, look at this increasing sequence, the heights of these splitting nodes. So now it's just, given some function, it's dense to, so you cannot remove these, but for the upper part, you can shrink the tree to make this tree arbitrarily thin, so that this gets a very fast function. So this height is going to be a dominating wheel. And so this is then clear in the final model. And I will refer to this dominating wheel in a moment by, say, D. So this is the generic dominating wheel added by the single step increasing sex amoeba forcing. So this is, D function in omega to the omega, just these heights. Similarly, you can, by just looking at the leftmost branch, you can prove that you can read off a wheel which is unsplit, and therefore the splitting number goes up in the final model. This is also quite easy. And so now for covering of meager. So what does this mean? This actually means that no Cohen wheels are added. If Cohen wheels were added, this would mean this is pushed up. And this is actually why you and your co-authors, so if you add this increasing property, then you prevent Cohen wheels from being added. So if you wouldn't have the property that these nodes are increasing, then you could play around with which of these nodes split first and encode some 0-1 pattern, and this would mean you add a Cohen wheel, very briefly speaking. But let's not go into details. Here we have something different. So to show that no Cohen wheels are added, it's you have to prove that it has the pure decision property. So actually A has pure decision, which means that given a Pn and many choices, a natural number n, and a name in n, then you can find a specific element in n and a pure extension, which means that you do not have to increase the number of fixed nodes. You leave the n untouched, but just shrink the tree, which forces this name to be this I star. So you can, between finitely many things, you can decide by just shrinking the tree. Okay. And from this, by elaborating this, you get a fusion version of this, and then you can derive the labor property. And actually, the labor property implies no Cohen wheels, and this covering of meager is small in the final model. So now I guess I have briefly talked or sketched this. So this is actually the main work now to show that the distributivity number h is aleph 1 in the final model. And I have only very little time, so I can only very briefly try to give an idea what's going on in the proof. So is it okay if I continue here? So as I said, we can define h by the maximal antichains. So what we do is we construct, at the end in the final model, a matrix of sets which witnesses then h equals aleph 1. So what do I mean with this? So we build a sequence A nu less than omega 1 of omega 1 many mad families, so maximal antichains in B omega mod finite. So these are mad families. And so let me draw a picture. So here's the first one, second one, and so on. So here's a mad family. The next one is like this. So I want to say that they are refining each other. So if you go down in this matrix, then for example, this antichain refines this. This means if you have a set here, that this set is almost included in this one. So this is the refinement property. And now if you have such a family of mad families, H equals aleph 1 is witnessed if there is no real intersecting it. So what do I mean with this? A intersects this matrix of mad families if for each line here, for each line nu, for each mad family, it's the case that we can find an element in it, a y in a nu, such that this set is almost contained in y, right? This is what it means, and we want that at the end we have a matrix for which there is no such A, that the matrix is not intersected, and this at the end witnesses that H is aleph 1. So let me from now on sketch what is the idea to prove this. So we have to carefully build the matrix, but let me first discuss if we would have such a, say by a single increasing sex amoeba extension, a new real which does this intersection, how would it look like? How could we read this real in a nice continuous way? So let's say we have a sex amoeba condition P which forces that A dot is a name for such an infinite subset doing this evil thing to the matrix. So now we look at the dominating real added by this, so the dominating real read off from the generic tree. And let me draw a picture. So here is, let's say we have 0, 1 here, and we consider, yeah, so what we do, so let's say P is P2, for example, so that this forces that for each n, the elements of A dot which happen to be in the interval given by the dominating sequence, so dn plus 1, that this is at most one element. It could be no element or one element, but we can always, without loss of triviality, shrink this A, then it even more intersects the matrix to have this property. Let's look at such a condition P2. This means we have already fixed these nodes, and let's look at what happens in there, in this interval from one height of the first splitting node to height of the second splitting node. So there is at most one element of A dot in there. Okay. So what are the possibilities? Either there is no element in there, so this is empty, or it's a singleton for one of these elements in the interval. So this means there are just finitely many options. So the interval is already decided by such a condition, but it might be that the condition does not yet decide which of these finitely many options is the case. So what we can do, we can apply the pure decision property to decide what is the case. And this is, by doing fusion all the time, we have to go through all possible extensions of such a condition to make sure that this is always the case. Once we have decided the interval, then already A within this interval is decided. And then by using actually which is also already needed to prove the pure decision, a lemma derived from the Halpern-Leukli theorem. We can do more. We can thin out the trees more to get that if we, so let's say, if we have now condition P, only P1, only this fixed, so let's look at what the next node could be. So the next node could be this, the next fixed node could be this node, or if the trees goes on like this, it could be this node, or this node, or this node, this node. So there's a whole perfect tree of possible next nodes sigma. So this would be the first example. So we can thin out things in such a way that the assignment from this node to what, if the interval is like this, the natural number is in there, so that we have, say, sigma to k sigma, which is this. This is an injective mapping from this perfect tree to the natural numbers. So actually I'm lying here. This is way more complicated. You have to consider several cases, but somehow it is as if we have always such an injective mapping. And what we now do, if we construct our matrix, we try to make the matrix immune to all kind of these attacks by such names which can be read like this. So let's first say if we have assigned the sigma to the k sigmas, then if this is coming from this condition P, then we define k of P to be the set of all these k sigmas. Sigma in these split nodes up here. And now, if the matrix were intersected by this real A dot, this would mean that for each given line gamma in the matrix, we could find an element y, as written here, such that A dot is forced to be almost in y. But since, as indicated here, so this set of k sigmas are potential next elements of such an A dot, it also follows that if, say, P forces this, that these potential next elements of A dot, Kp, are all in Y, almost, roughly speaking. So what does this mean? So this is now a set from the ground model, this assigned potential next elements. This is almost in Y, and so by the refinement property of the matrix, it's almost in or disjoint from all the elements in the mat families up here. So this is not a contradiction yet, but this can be turned into a contradiction once we have built the matrix in such a way that we prevent this from happening. So what do we do? And I can end with this in 2 minutes, I guess, or less than 2 minutes, so that we have to go through, when building the matrix, all Sachs amoeba conditions together with all kind of labelings, injective labelings of such k sigmas. Under CH, these are just omega 1 many. And for each element we have built the matrix so far, we look at whether this corresponding set KB does already yield the contradiction, so there are already problems in there and that it's not almost contained or almost disjoint, or if we can arrange it in that way that it is almost contained or almost disjoint, then we can add it to the matrix without destroying the AD property or the refinement property. Actually, we have to add a whole Cantor scheme and so on, but once we have done this, at the end there will be a contradiction, because on one hand it's almost contained or almost disjoint. On the other hand, we have prepared our matrix in such a way that this is just not the case. And this is the final contradiction. So one last minute. So far I was only discussing the case why a single increasing sex amoeba forcing does not add such a real A intersecting the matrix. But then for the whole iteration, you can actually modify this a little bit just by using that the tail of the iteration has the Lever property. The single forcing has the Lever property, this iterates, so this is fine. This is still only a matrix in the ground model, which is not intersected now at the end in the final model. But then, okay, you have to do it all the iteration that you can, you have to extend, so to speak, all the mat families to the right here, keep it omega-1 many lines, but extend it to get at the end really mat families which are not intersected in the final model, and this actually gives then the witness for H equals L of 1 in the final model. Okay, so I can add this.